Okay, so yesterday I showed you the beginnings of what a reaction looks like. You start with a reactant, and then what happens when a reaction happens is you've got to put energy into that system. For those of you who had lab yesterday, you know that to start the Bunsen burner, we had to have a spark. Okay, so that's the energy that got that reaction going. So, what happens with that spark is it takes apart the reactants. Molecules. That means bonds are broken. And that's why it required energy. You've got to break those bonds. And then what happens here is you've got a complex of taken apart reactant atoms. And there's a fancy name for that. That's called the activated complex. Okay, so that in the middle there are the atoms from the reactant that are broken up by the energy put into the system. And that's one of the things called the activated complex. Now, two things are going to happen now. Most of the time, you don't see a double arrow, but all reactions, no exceptions, have two arrows. What happens is that mixture of reactant atoms reforms the reactants. So you get some that go back this way, and then some that go to the product. You have this mix. And there's a whole unit in Chem 1A. What happens is it ends up with a mixture of products and reactants. And that mixture is determined by something called equilibrium constant. Don't worry about that. The main thing is when you throw energy into that system, things break up and you reform. Now, what makes them form into products is how stable those are. So if the products are more stable than the reactants, you get more product. If the reactants are more stable than product, you get a little bit of product, not a lot. And that's where that equilibrium comes in, depending on what you're trying to do. Okay. What's also required is a mass conservation. Start with 5 grams. Guess how much you end up with? 5 grams. Now that 5 grams is a mixture of reactants. And that 5 grams in the product side is a mixture of products. And products are not the same as reactants. They have the same atoms, but the mixture is different. The connections are different. And that's what makes one more stable than the other, is that combination. So if we start with 5 grams and we end with 4 grams, we're gonna have a big explosion. So E is equal to MC squared. And we have a big explosion. No, it's not good. Okay, so when I say we have to conserve mass, when it comes down to is really we're conserving atom. Okay, let me real quickly do some house cleaning here. Okay, so this chemical equation and then we'll move to the products of that reactor. You have a mixture of product and reactor. Now, it's conservation of mass bit. What happens is things are not going to be taken apart mass-wise. They're going to be taken apart via inventory of atoms. So we're going to, first thing we're going to do is inventory what we're starting with. And we start with reactants. So let's start with methane and oxygen and burn it. It's like in lab today and yesterday. Gas comes out of the wall, natural gas. We mix it with some kind of oxidizer, in this case oxygen, and we form oxidized reactant, in this case carbon dioxide and water. Now, inventory, what does that mean? Well, we got inventory the reactants on the left, got inventory the products on the right. So the way I do it is, in my opinion, very straightforward. So what do we have atom-wise? Well, we've got some carbons, we've got some hydrogens, and we've got some oxygens. How many carbons are on the left? We're doing the inventory now. 1. How many on the right? 1. So we're in good shape now. How many hydrogens on the left? 4 on the right. 2. Not good. Oxygens on the left. 2. Oxygens on the right. 3. Okay, so this is not a balanced equation because left is not equal to right. Now, when we do the inventory, we are going to conserve mass at the same time. But it's hard to conserve mass. It's easier when you do it by atoms. That's why the balance equation is atoms. Someone had a question.
It always should be balanced, yes? It always should be balanced.
Yeah, that's the goal. Balance. Like life. What? Balance and life. Okay, so now we got to do some things to make it balanced. There are 2 sets of numbers in this deal. We've got those numbers, the subscripts, and we have a number in front, and those are called coefficients. The only numbers we're allowed to change are coefficients, not subscripts. If we change the subscripts, we're changing the molecule. We're not changing molecules on either side. We're only changing the number of molecules, not the numbers of the constituents. In other words, if we make this CH2, it's no longer methane. We can't change H. Methane is not saying methane. But we can't change the number of methane, the number of oxygen we have, the number of carbon dioxide, the number of water. And again, we cannot change substance, only coefficients. Now, if you notice, there are no numbers in front. So it's assumed that it's 1. Now, I'd recommend balancing equations with a pencil. You can do it with a pen. Pencils are better. Okay. So let's balance this guy now. First of all, we don't have to worry about carbons right now. Let's deal with the hydrogens. Okay. Hydrogens come by 2s on the right side. Hydrogens come by 4s on the left side. So what coefficient can we put instead of a 1 on the right? 2. Now we have to take inventory again. That gives us 4 hydrogens, 4 oxygens, 1 carbon. Okay, the hydrogens are in good shape, and we have to deal with the oxygens. Okay, we've got 4 oxygens on the right. They come in 2s on the left. How many do we need on the left? 2 more or 4 total, right? So if we change the 1 to a 2, that'll give us 4 oxygens. What? Okay, now let's balance. No, I didn't say this is a technique. What we're doing is we are guessing and checking. We check by doing inventory. That's pretty much. Now, whenever we do stoichiometry problems next week, the first step is if there's a reaction, balance the equation. Is there a question?
No, I was.
Fixing your hair. Okay, so does this make sense? Now, if you've never done this before, this takes lots of practice. I have 7 worksheets on Canvas for you practice. Again. Now let's do some more of these. Let's burn ethane. Ethane is a 2-carbon hydrocarbon. Let's burn it in oxygen. Okay. Step 1, inventory. Okay, we have 2 carbons, 1 carbon. 8, 2, 2, 3. So we are all over the place. Now, one suggestion when you're balancing equations, leave the little guy left. Start with the most complicated one first. Okay, so this is probably the most complicated. All right, so what we've got is well, we've got what here? 2 carbons. What can we do over here to get 2 carbons? two out front of the carbon dioxide. Do inventory again. Okay, that gives us 5 oxygens, 2 carbons, 2 hydrogens. Nicholas, the real formula for ethane is C2H6, not 8. I mean, we can still balance it, but it wouldn't be a real molecule. Okay, so, carbon. Now leave the little guys for last. Let's do the oxygen last, because it's a small molecule. So let's do H's next. Okay, what do we do on the right side to bring those H's up? With 3 there, that'll kick the H's up to 6. Oxygens now are 3 and 4. Everyone see where we got 7 oxygens? 7 total oxygens on the right. But what's left? Oxygens. They come 2s on the left. How do we get 7 oxygens that become by 2? Okay, so this is where my technique differs slightly. I would say half the chemistry teachers are going to tell you to do it my way, the other half are going to do it something different. Okay, my way is, what do we multiply 2 by to get 7? 3.5. 3.5 times 2 is 7. So if we, and instead of 3.5, we're going to make it what? What is 3.5? Let's make it that. Okay. It's 7 times 2. Oh, 7 over 2 times 2 is 7. Now, this is the part. So is this balanced? Yes. Why is it balanced? Because the numbers are equal on both sides. However, you can't have fractional coefficients. So we just fix that right now. How will we fix that? Getting rid of that fractional coefficient. Anyone have any ideas? Yeah. Multiply everything by 2. Perfect. Multiply everything by 2. Think of this as an equation. What we do to the left, we do to the right. So 2 times 1 is 2. 2 times 7 halves is 7, 6, 4. Now, if we take inventory, it's going to be 4, 14, 12. And over here, we've got 12 H's, 4 carbons, and 6 and 8 is, this is not 12, it's 14. Oops, what not? 6 and 8 is 14. Okay, so now it's balanced because left and right, plus we have no strength. Okay, so you can have fractions and you're all going to get rid of it. Okay, now that is seemingly the process. So you take inventory, change, inventory, change, inventory. Do not change something without retaking inventory. Because frequently you change one thing, you change another as well. Except when it's all simple. All the others You don't take inventory, these numbers are gonna be off, and we should check everything. Now, who's interested in extra credit? A few of you, okay? If you go to files. Um. This is an extra credit. Equation to balance. Now, if you've never balanced equations before. I'm not trying it. Most people take about an hour and a half to balance it. That's like credit. You don't get afraid of big coefficients. When I say big, I'm talking about like over 100. Okay? So this seems like a simple equation, but it's not. Okay, and if you're interested in doing that, we'll do that, and when we do our next steps, just turn it in. Then put to the back end. Okay, so let's practice some more here. And this is a file on Canvas. Unit 3 periodic table. Okay, so let's now on your next test, you're going to have the focus of this unit called work down. Half of first time your problem, the other half is what we did yesterday. What's given, what you try to calculate, and we do some cancellation. So this part is as important as history. Because if it's not balanced, everything is off. Okay, so why don't you try oh, I don't know. Let's see, what would be a good one to do here? Let's do gasoline. Okay. Try doing that one on your own. Might be easier on your name.
Oh.
Huh?
I know we have this.
That's kind of rough. Been there, done that. Okay. So let's go ahead and do this here. Inventory goes first. Okay, so we took an initial inventory. Okay, so we have 8 Cs on the left, 8 Cs on the right. Okay, so we end up with 16 O's plus 1, 17 O's. Okay, we have 18 H's. 18 H's. And we've got 16 and 9 is 25. Okay, now we're gonna have to deal with that O2 again here. So we have even and odd. Whenever you have this even and odd bit, think fractions. Okay, so what do we multiply 2 by to get 25 like before? 25 over 2 gives us 25. What?
Because it gives us 15. Not the 15. We need to put 46 over 2. Huh?
46.
Over 2 to get the 25.
46 over 2 is what?
It's gonna be 23 and we have 2. Yes, we need to get 25.
So multiply 25 over 2 times 2. Each canceling this.
Oh,
Now it's balanced. Why is it balanced? Left equals right. But you can't stop here because there's a fraction in this location. I'm going to show you in a minute why you can't have a fraction. Okay, we multiply everything by 2. Again, think of this as an equation. What you do to the left, you got to do to the right. And that clears the fraction. So we end up with 50 oxygens, 36 hydrogens, 16 carbons, 16 carbons, 36 hydrogens, and 18 and 32 is 50. So let's talk in general about once we have a balanced equation, it gives us two things. And it doesn't give us another. Okay, the two things are a molar relationship between reactants and product. And that relationship is the coefficient ratios. Notice how moles keep coming back into this. So if we look at this equation, the first one we looked at here, what I just said as it applies to this equation now, it says that 1 mole of methane will react with 2 moles of oxygen, giving us 1 mole of carbon dioxide and 2 moles of water. Okay, so it's a molar relationship of the coefficients. Now, what do you- Wait, probably put all this together. And that's gonna be the middle step in every single stoichiometry problem. Is looking at ratios of coefficients. And that's why we balance it, so that. 2 moles of this reacts with 7 moles of oxygen. 6 moles of water, 4 moles of carbon dioxide. Now, let's look at gasoline. With gasoline. Now, gasoline is a mixture of a bunch of stuff. It's mostly octane. That's all. So for 2 moles, we have 25 moles of oxygen. Now, air is not all oxygen. It's a mixture, mostly nitrogen, not oxygen. It's about 40%. Less than probably about 25% oxygen. So we need 4 times this amount. So really we need 100 to 100. That's why your air cleaner is really important on your car to keep it clean. Because we suck a lot of air through the air cleaner. A gallon of gas is not 2 moles. A gallon of gas is a lot more than 2 moles. So keep this equation in mind for maintenance on your car. Clean your air filter or replace it. It's really important. Gas mileage will benefit. Modern cars and computers kind of compensate for this. They compensate by keeping the mixture at a certain ratio for optimum economy of power. But they're going to keep it clean. Now, that's one thing balanced equations give us. The other thing is a molecular. Molecular relationship. And it's the same thing. So instead of moles, we're talking about molecules. So everywhere up here, you have a mole and then molecule. That's why mole and molecule are so closely related. That's why they came up with mole for the word molecule. So we have 2 molecules of octane reacts with 25 molecules of oxygen, giving us 18 molecules of water and 16 molecules of carbon dioxide. Now, mass relationship is not valid other than total reactants equals total product. Yeah. In terms of the individual reactants and products, mass is not valid. So what do we mean by that? Is 2 grams of octane does not react with 25 grams of oxygen balance. In order to give you 18 grams of water, 16 grams of carbon dioxide. The mole relationship, a molecule relationship, not a mass relationship, okay? So if I have a problem, a stoichiometry problem that says, 25 grams of octane reacted with how much oxygen? That is a typical stoichiometry problem. So what do? With mass stuff, what do? Convert it to, no, valve. So that's the essence of these three statements, is we can't work in anything but moles or molecules. Most of the time it's going to be moles. Okay, so why we balance equations is for this relationship. Now we have a molar relationship between everything. But only after we balance it. It's not valid unless it's balanced. And if something is in mass or liters or a number of molecules, you have to convert it to mole. Then we can talk about relationship, okay? That is fundamental to stoichiometry. We've got conversion to mole. This is mole of heating it to death. We continue to do it to death for the rest of the semester. Okay. Now we just need to practice it a zillion times. So,